This is a video about a certain classification tool of groups, and that classification tool is a decomposition of a group into a so-called composition series or a certain type of subnormal series. But let's look at some definitions so we know what we're going with here. So throughout the video, G will be a group, and a subnormal series of G is a sequence of subgroups. So let's see what we have here. We have over here on the left-hand side is the trivial subgroup, which is just the subgroup containing the identity. We'll call that H0. Then H0 is a subgroup of H1, which is a subgroup of H2, all the way up. Hn minus 1 is a subgroup of Hn, and Hn is equal to G. And we call this a subnormal series if Hi is normal in Hi plus 1. So at each stage right here, we have a normal subgroup relationship. But it's well known that normality of subgroups is not transitive. So this condition right here does not tell us that all of these subgroups are normal in G. Okay, so anyway, now let's look at some special conditions or types of subnormal series. So let's say we've got two subnormal series of a group G. Then they're said to be isomorphic if, when we look at the list of the corresponding quotient groups, so whenever you've got a normal subgroup, you can always think about taking the quotient group. So anyway, these lists of quotient groups are the same. So they're going to be the same up to some sort of permutation. And then, well, our next thing is, well, what does it mean for a subnormal series to be called a composition series? Well, it's called a composition series if each of these quotients is simple. Let's recall that a simple group is a group where there are no normal subgroups. I should say non-trivial normal subgroups. So the only normal subgroups of a simple group are the trivial group and the whole group. Next, G is called solvable if it has a subnormal series where each of these quotients is abelian. Okay, so let's go ahead and look at some examples. So notice these are two subnormal series. The first one is for the dihedral group D4. So we've got this group right here generated by R squared and S. So that's normal in D4. We know it's automatically normal in D4 because this group has 4 elements, whereas D4 has 8 elements, which means the index is 2. But whenever the index of a subgroup is 2, the subgroup is normal. And then here we've got the cyclic group generated by the reflection S. So that'll be order 2. So since this is order 2, it's normal in this subgroup, which is order 4. So we've got a subnormal series there. Then we could have another subnormal series like this. So the trivial group here, the alternating group on n letters here, and then the symmetric group on n letters there. So it's well known that the alternating group is simple in the symmetric group. But if n is bigger than or equal to 5, an is simple. So we couldn't like extend this off that way if we wanted to because there are no normal subgroups to put inside of an. Now let's look at two subnormal series of Z60. And throughout this, we're going to use this fact that in Zn, the cyclic group generated by M is isomorphic to Zn divided by the GCD of M and N. That allows us to know the isomorphism classes of all of these subgroups in the middle. So let's just look at this. So notice that 60 divided by 3 is 20. So this is isomorphic to Z20. Then let's see, this is going to be isomorphic to Z10. This right here is going to be isomorphic to Z5. And well, this is just the trivial group here. And then over here, we've got something generated by 20. So that's going to be isomorphic to Z3. This one will be isomorphic to Z15. This right here will be isomorphic to Z, let's see, it'll be 30. And knowing the isomorphism classes of those subgroups will help us easily calculate the quotient groups. Okay, so let's look at here Z60, which is the top group, modded out by this cyclic group generated by 3. So we know that's going to be a group with 60 divided by 20 elements. It's going to be a group with 3 elements, but all groups with 3 elements are cyclic. Well, actually, all quotient groups of cyclic groups are cyclic, so we know it's going to be cyclic anyway. So that makes this isomorphic to Z3. And then let's see, if we've got the cyclic group generated by 3, quotiented with the cyclic group generated by 6, well, that's going to be something with 20 elements, quotiented with something with 10 elements. So in the end, we'll get Z2. And then let's look at Z10, or sorry, the cyclic group generated by 6, mod out the cyclic group generated by 12. Again, that's going to be another copy of Z2 for essentially the same reason. And then finally, we've got the cyclic group generated by 5, mod out with the trivial group. So that's simply going to be equal to Z5. I think I said the cyclic group generated by 5, I meant generated by 12. Okay, so there's our list of quotient groups. Now let's go over here in this direction and just start with Z60 mod the cyclic group generated by 2. But let's observe that that's going to be isomorphic to Z2 for the same sort of argument we've been making. And then we'll do the cyclic group generated by 2, mod out the cyclic group generated by 4. So that's going to be another copy of Z2. And then let's see, the cyclic group generated by 4, mod out the cyclic group generated by 20. So that's going to be a copy of Z5 using our argument that we've been using. And then finally, the cyclic group generated by 20, mod out with the trivial group. So that's going to be Z3. But check it out. All of these groups over here on the left-hand list are the same as the groups over there on the right-hand list, up to isomorphism, of course. So notice that this Z3 is that Z3 down there. This Z2, well, there's a Z2 up there. This Z2, well, there's a Z2 right there. And finally, this Z5 corresponds to this Z5 right here. So that means that, well, not only are these two composition series, but these two composition series are isomorphic. And in fact, that's not an accident. And that's actually the big result of this video, is that we'll show that all composition series of groups are isomorphic. Or in other words, there's a unique up to isomorphism composition series for each group. But we're going to look at some more examples before we get there. Okay, so now we're going to prove that every finite group has a composition series. And then we'll look at an example of an infinite group with no composition series. Okay, so let's get going. So let's say that G is a group, and let's say that N is a natural number such that N is the largest length of all subnormal series of G. So in other words, you look at all subnormal series of G, and among all of them, you find the one that is longest, or you find one of the ones that is longest. And I guess I should say here that we know that a subnormal series exists because, well, there's a trivial one that just does identity and then the whole group, and that satisfies these rules of a subnormal series. Okay, so now let's take one of these subnormal series of length m, or sorry, n, I should say. So it starts with the identity, which is H0, which is a subgroup of H1, which is a subgroup of H2, so on and so forth. All of that's a subgroup of Hn minus 1, which is a subgroup of Hn, which is equal to G. But now what we want to do is show that this subnormal series, this longest subnormal series, is in fact a composition series. Which means what we want to show is that for all appropriate I, hi plus 1 mod hi is simple. And we can do that by taking a normal subgroup of hi plus 1 mod hi and showing that that normal subgroup must be either the whole group or maybe the trivial group. So let's see how we might do that. So let's take a normal subgroup. I'm going to call it K, which is normal in hi plus 1 mod hi. But then by a correspondence theorem of normal subgroups inside of quotient groups, that means that there exists an n, which is normal inside of hi plus 1, such that k is equal to n mod hi. So again, that's by this correspondence theorem for normal subgroups. But now what we can do is just slot that in between hi and hi plus 1 in our series. So let's see how that goes. So we've got E, which is the subgroup H naught, which is the subgroup of H1, all the way up. We've got Hi here, which is a subgroup of N, and that's a subgroup of Hi plus 1, so on and so forth, all the way up to Hn, which is equal to G. Okay, but then by the longest condition, we know that that means that the normal subgroup is either equal to Hi or the normal subgroup is equal to Hi plus 1. Okay, but then let's see. If the normal subgroup is equal to Hi, then that means that K is equal to Hi mod Hi, which is just the trivial group inside of Hi plus 1 mod Hi. So again, in this case, we started with a normal subgroup and we got that it's the trivial group. Now let's see the other case. So if n is equal to Hi plus 1, then that means that K is equal to Hi plus 1 mod Hi plus 1, which is equal to Hi plus 1 mod Hi plus 1. So, but that's the other case. So notice we've got K, a normal subgroup of this, but then that means that K is either the trivial subgroup or the whole group. But that's what it takes to show that this thing is simple, that those are the only two possible normal subgroups. Okay, so anyway, we've just shown that every finite group has a composition series. Now let's look at our example of an infinite group with no composition series. And we don't have to go very far. All we'll do is show that z, the integers with addition, does not have a composition series. So let's do this by way of contradiction. So by way of contradiction, let's suppose we have a composition series. But since we have a composition series, that means that H1 mod H0, which is simply equal to H1 mod the identity subgroup, which is really just isomorphic to H1, is simple. Okay, cool. So let's see, that's really two things here that are important. So let's see what those two things are. So first of all, H1 is a subgroup of Z, and H1 is simple. So we have a simple subgroup of G. But we'll see that that pretty much quickly gives us a problem. So if H1 is a subgroup of G, that means that H1 is equal to, well, let's see, we'll write this as mz for some m, which is a natural number. So that's by just a classification of all subgroups of Z. They're all cyclic. Maybe if you want to write that as the subgroup generated by m like that, that would be also totally fine. But now notice that we can immediately see that H1 is not simple. And how could we do that? Well, notice that if we take 2m times z, that's going to be normal inside of m times z. So it's pretty clearly a subgroup, and then it's a normal subgroup because everything's abelian. So every subgroup is a normal subgroup. Maybe if you want to convince yourselves that this is a subgroup, notice that it has all of the elements 0, plus minus 2m, plus minus 4m, plus minus 6m, so on and so forth. Whereas this thing right here has all of the elements 0, plus minus m, plus minus 2m, plus minus 3m, so on and so forth. So it's clearly a subgroup. And then again, like I said, normal because everything is abelian. But that contradicts its ability to be simple in the first place. Okay, so now let's get going with the big result, the so-called Jordan-Holder theorem, which says that any two composition series of a group are isomorphic. All right, so like I said, now we're going to look at this thing called the Jordan-Holder theorem, which says that any two composition series of G are isomorphic. Recall that composition series are isomorphic if, when you take the list of the quotient groups for both of the series, well, that list is isomorphic, up to permutation, of course. So we saw that in our example before. Okay, so this is going to go by induction on the length of the series. So the base case is pretty simple. We have a length 1 series, which means that G must be a simple group. Now let's move into the induction step. So let's suppose the statement is true for all series of length k, which is between 1 and n, not including n. And now let's consider two composition series. So let's write them out. So the first one will go E, which is equal to h naught, which is less than h1, which goes all the way up to hn minus 1, which is a subgroup of hn. I think I said less than, but I meant a subgroup. Good. And then, so that's our first series. And then our second one will be with subgroups k. So we've got K0, a subgroup of K1, all the way up, a subgroup of Km minus 1, a subgroup of Km, which is equal to G. And now the idea here is we're going to modify these two composition series. And we're going to do it in the following way. So let's take this first one and we'll intersect everything in this first one with Km minus 1. Then we'll take this second one and intersect everything with Hn minus 1. And then we'll actually extend it out a little bit as well, but we'll see that. So here we're going to have the identity subgroup, which is equal to H naught intersected with Km minus 1, which is a subgroup of H1 intersected with Km minus 1. All the way up, we have Hn minus 1 intersected with Km minus 1, which is a subgroup of Hn minus 1, which is a subgroup of Hn, which is equal to G. So see how we extended that out a little bit? We put this copy of Hn minus 1 near the end, not intersected with our Km minus 1. Okay, now we're going to do kind of the same thing for the next one. So here we'll have E, so that's going to be, let's see, K naught intersected with Hn minus 1, a subgroup of K1 intersected with Hn minus 1, all the way up, a subgroup of Km minus 1 intersected with Hn minus 1, a subgroup of Km minus 1, a subgroup of Km, which is equal to G. Okay, so now we've got that going on there. Okay, cool. And now what we want to do is look at a quotient. Let's see, it's going to be from this first series up here. So a quotient is going to look like this. So it's going to be hi plus 1 intersected with Km minus 1 mod, and then hi intersected with Km. Good. But now I'm going to do something here, and I'm going to take this hi, and I'm going to move it out here, and then in the middle, I'm going to put hi plus 1. And I can do that because we know hi is contained in hi plus 1. So essentially what I'm doing here is I'm exchanging hi for the intersection of hi with hi plus 1, because those both are the same. But now what I can do is look at this and observe that this looks like something that would have been in the second isomorphism theorem. So make sure to go check out the second isomorphism theorem if you need to recall what that looks like. And then this is going to be hi times the subgroup hi plus 1 intersected with Km minus 1 modded out by hi. So that's what the isomorphism gives us in this second isomorphism theorem. But now let's observe that this right here is a normal subgroup of hi plus 1 mod hi. So I think that's pretty clear because the so-called numerator here is normal in the numerator over there. That's because we've got HI here, which is normal in HI plus 1, and then this right here is a subgroup itself of HI plus 1. Okay, cool. But then since this is a subgroup of this, and we know this thing over here, HI plus 1 mod HI is simple, that means that this group on the top here must either be equal to the group on the top here, or it must be equal to the group on the bottom there, because simplicity in being a normal subgroup means that this group right here is either the whole group or the trivial group. So let's write that out. So what do we get out of that? So like I said, we've got this HI times HI plus 1 intersected with KM minus 1 is equal to HI. So that's the case when this is really the trivial subgroup, or HI plus 1. So that's the case when it's the whole group. Okay, so now let's talk about this. So if every one of these is equal to HI plus 1, then that means that Km minus 1 intersected with HI plus 1 must be equal to HI plus 1. But that's going to only occur when Km minus 1 is exactly equal to Hn minus 1, and thus we could have just applied induction from the beginning. So that means at least one of these is equal to this Hi. But if one of these is equal to this Hi, then that means, well, we could have gone to our subnormal series right here and notice that we've got repeats in here in the middle. So since we've got repeats in there in the middle, we can remove them. So let's say that this squiggly arrow is the removing of those repeats. And that's going to give us the following subnormal series, or composition series, I should say, which goes like this. So E0 is equal to H0 intersected with Km minus 1, all the way up to Hn minus 1 intersected with Km minus 1, and then Hn minus 1. We're going to cut it at Hn minus 1. Okay, so let's look at this carefully. So it looks like that's going to have length n, and that the induction hypothesis is not applicable. But by our discussion that we just had, we were able to remove some of these subgroups in the middle, which means this really has length less than n, and that in fact we can apply the induction hypothesis. Again, because it's so-called short enough to apply the induction hypothesis. So that means we've got a composition series that's short enough of Hn minus 1. But that means that it is equivalent or isomorphic to the composition series of Hn minus 1, which we get just from truncating our original composition series. So this is equivalent to the composition series starting at E, which is H naught, a subgroup of H1, all the way up to Hn minus 2 with Hn minus 1. And then what we can do is just put the G back on these two. So let's see, this, which ends at Hn minus 1, is equivalent to this that ends at Hn minus 1. So now if we throw the H, and that's by induction, but then if we throw the Hn back on, which is equal to G, we get our composition series for G. But then that just throws on some equivalent things, meaning that we still have an equivalent composition series. So now let's see where this is going to take us. So we just finished showing that this composition series that I have in magenta is equivalent to the composition series that we have in blue. And then furthermore, we also argued that Hn minus 1 was not equal to Km minus 1. And we did that because if they were, we could have just done induction at the very beginning on our original two series and been done. Okay, so let's see. This inequality of these two subgroups now implies that we have Hn minus 1 is a proper subgroup of Hn minus 1 times Km minus 1. We know this is a subgroup because both of these are normal in the whole group because they're at the top of the composition series. Okay, cool. But then since they're both normal in the whole group, that means their product is also normal in the whole group. But now we can take the quotient here, and what will we have? So we'll have hn minus 1 times km minus 1 mod hn minus 1 will now be a normal subgroup of G mod hn minus 1. But we know that G mod hn minus 1 is simple. Of course, we know that this is not equal to this product. This hn minus 1 is not equal to this product. So this cannot be the trivial subgroup. So since it's not the trivial subgroup, it's the whole group. But if it's the whole group, the, for lack of a better term, numerator groups are the same. So in other words, we have hn minus 1 times km minus 1. The product of those two groups is in fact equal to all of G. And now we're going to apply the second isomorphism theorem again. And what is that going to give us this time? So now let's look at km minus 1 mod out by km minus 1 intersected with hn minus 1. And let's observe by the second isomorphism theorem, like I just said again, that's going to be the product km minus 1, hn minus 1, mod out with hn minus 1. But we just said that that product was G, so this is G mod hn minus 1. But now that pretty quickly shows that this blue boxed normal series, or composition series, is equivalent to this one underneath it. So those two are equivalent. But then by a parallel argument showing that magenta and blue are equivalent, we get that the one below magenta is equivalent to the one below blue. So that gives this like chain of equivalences. So this one under magenta is equivalent to this one. We just showed that this one is equivalent to the blue one. Earlier we showed the blue one was equivalent to the magenta one, meaning the two that we started with are equivalent. But the two that we started with were our arbitrary 2 composition series. So we showed that our arbitrary 2 composition series were in fact isomorphic. But that's where we wanted to end up. Okay, so now I want to look at some examples of solvable groups and maybe prove a nice result, which is another way of thinking of this definition of solvability of a group. Okay, so now for our examples, let's start by showing that all dihedral groups are solvable. And in fact, this is pretty easy because we can just take the following subnormal series. So we're going to take the subgroup generated by a single rotation, and that's just inside of Dn. So let's observe that the subgroup generated by the single rotation is Zn, which is abelian, and then it's index 2 in Dn, which means the quotient group is Z2, which is also abelian. And that's really all we need to do here. Now, let's also prove that the symmetric group Sn is not solvable if n is bigger than or equal to 5. So it will be solvable in the n equals 4 and 3 case, but it's not solvable after that. And how can we show that? Well, let's observe the following. So if n is bigger than or equal to 5, then an is simple. So that's a well-known result. And then also an is normal in Sn. It's index 2. So, well, that tells us that the following, starting at the trivial group, then going towards an, and then going towards Sn, is a composition series. Okay, but let's think about this. By the proof that all finite groups have a composition series, we know that composition series are the longest possible subnormal series. So that means every subnormal series of Sn is either length 1 or length 2. Well, here's one with length 2, but notice that our quotient here, an, with this trivial group is not abelian. But then if we had a length 1, well, then we would just have, let's see, this the trivial group up to Sn, but then our quotient is also not abelian. So it's important that we had to use a couple of those results to get there. I guess we also use the fact that by our previous theorem, this is essentially the only composition series. Okay, so anyway, let's take a step back and see what we did here. So because AN is simple, we know that this is a composition series. But then since composition series are unique up to isomorphism, this is the only composition series. But then since composition series are the longest possible subnormal series, the only other subnormal series is this down here. But neither of these subnormal series, the only two possible subnormal series, give us quotient groups that are abelian, which means there is not a subnormal series where the quotient group is abelian, which means Sn is not solvable. Okay, so now let's see about this other definition of a solvable group. So towards this result, let's recall a definition. So if G is a group, then the derived subgroup, sometimes G prime or the commutator subgroup, which we'll call G upper parentheses 1, is the group generated by A inverse B inverse AB, where AB comes from G. It's important that it's generated by that, meaning every element of this is a finite product of things that look like this. We won't use that here, but that's just something to keep in mind. And then we can recursively define G upper n plus 1 as G upper n upper 1. And now the result says that G is solvable if and only if there is an n where G upper n is the trivial group. Now, we're going to use some facts from some standard homework exercises, which hopefully you've done before. If you haven't, I would urge you to do these homework exercises. So the first is that G upper n is a normal subgroup of G upper n plus 1. And then next, if you've got a normal subgroup K of H, and H mod K is abelian, that's equivalent to H upper 1 is a subgroup of K. Okay, so let's get going with the proof, starting with the reverse direction. But then observe that we can just form the following subnormal series immediately. So it starts at E, which is equal to G upper n. G upper n is contained in G upper n minus 1, so on and so forth. We've got G upper 2 here, G upper 1 here, which is contained within G. But then all of those quotients are abelian by this condition right here. Because notice, H upper 1 is contained within itself. That implies that H mod H upper 1 is abelian. But each of these quotients, as you go down the line, is really just exactly that given our recursion. Okay, so I'll just maybe put a note here, and that is G upper I plus 1, or that would be I minus 1, the way we're doing it, mod G upper I is most definitely abelian. Okay, cool. Now let's look at the reverse direction. And so in the reverse direction, we're going to suppose that G is solvable. But if G is solvable, then we have a subnormal series where those quotients are abelian. So let's look at our subnormal series. So we've got E, which is H naught, which is a subgroup of H1, subgroup of H2, so on and so forth. Up here, Hn minus 1, which is a subgroup of Hn, which is equal to G. And this is with the condition that Hi plus 1 mod Hi is abelian for all appropriate I. Okay, nice. But then if that is abelian, that means that Hi plus 1 upper 1 is contained within Hi. Again, by our condition over there. Okay, great. But now we can just kind of get going with it, starting at the top. So let's see. That means that H upper 1 of n is contained within Hn minus 1. But since Hn is G, that means that G upper 1 is contained within Hn minus 1. And then I think you could see where we're going here. We're just going to apply the upper 1 thing again, and that'll give us G upper 2 is contained within G upper 1, which is contained within H upper n minus 1 upper 1. But then that's going to be contained within Hn minus 2. But now we can keep stringing this out until we get down here. So we're going to have G upper n will be a subgroup of H0, which is equal to the trivial subgroup E. But that means that G upper n is the trivial subgroup, but that's where we wanted to end this direction. Okay, now I'm going to leave you with some exercises. All right, so here are some exercises. So the first is to find all composition series for these three groups. Z48, D6, and Z4 cross, let's see, that should be S3. Next, let's show that S4 is solvable. So that makes it different than S5, S6, so on and so forth. Next up, let's suppose we've got a normal subgroup N of G. Let's show that if N and G mod N are solvable, then G itself is solvable. And that's a good place to stop.